Point, the four terms are not the same. They're often confused. Whether it's like a resource or a use case, I don't know. I mean, you can call it a sort of scarce, an artificially scarce asset, I suppose. I think a resource is maybe a little bit iffy. These are Sean's slides. But blockchain technology, yes. DeFi, vertical, absolutely. And Web3 is our approach in order to create resilience. What do we mean by resilience? Very interesting sort of question. There's a lot of different things that we need to be resilient against. Some like pretty obvious ones like hacks, security, network outages, absolutely. Ownership disputes can be quite. Definitely got some experience in that. And actually something that isn't mentioned here but is quite important is resilience against the creators of the system. Like most of the time, especially in like traditional sort of practitioning, there's just an assumption that the creators of the system, it doesn't need to be resilient against those guys. They created it. Why would they ever want to harm it? And actually, this has been taken to incredible levels of presumption. For example, any country that has bought the F-35 fighter jet, America's, up until not very long ago, top fighter jet model, had to get a monthly software update for that fighter jet or it would stop working, right? So there's just a presumption by the purchasers of that the creators of it are, they don't need to be resilient against the creators of it. The creators will always, be on their side or be on the side of this thing working, which is nonsense. It's total nonsense. A lot of the nonsensical presumptions that society is sort of, particularly surrounding technology and international sort of technology, is going to be they're going to be uncovered quite starkly. I mean, we're already seeing some of that, but I think we'll see more and more. Why are we banging on about like not trusting, trustlessness, trust freedom? Why less trust? Basically, because people are bad. They're not bad, but they're opportunistic and to some extent don't care that much about right and wrong, especially if they're powerful people, because it doesn't sort of affect powerful people so much. They're less reliant upon other people, I suppose, because they have power / money / whatever. And so when you're in this sort of position of being very powerful, and especially if the power leads to an accountability, then you can really abuse that trust. And it's nothing new, right? It's like really well understood. Not controversial at all, yet somehow we've ended up in a world where most of the technology that we rely on to live our lives is bound by trust. It's like mad. We're in a mad situation. Examples, you don't really need to go into them. I'm sure they're all familiar with you by now. So how do we describe Web3? Well, there's a few different ways. Sean's properties of Web3, I've got my sort of blockchain maxims. Andreas had his blockchain things. And I think they're all sort of dancing around the same broad concept here. Sean's a little bit more focused on the sort of nuts and bolts. I guess Andreas is a bit more sort of political and philosophical. And I'm a little bit more technical. But, Web3 is about how people interact with the world of people really, but to some extent devices as well. This is a very interesting point of Web3 and something that I kind of realized quite early on in this industry. We were developing device automation, like not automation, automation, device automation, making devices autonomous. This is what blockchain is doing, really. This is what Web3/blockchain is doing, right? It's giving devices the ability to basically be regular economic actors in the world. Yeah? They don't need to go to a human to entrust their, I don't know, assets or whatever, identity to. They kind of have it, they're self-sovereign. Now we talk about us being self-sovereign, Web3 sort of enabling self-sovereignty. But actually, you know, and this wasn't thought about so much 11 years ago, but actually it's not just enabling it for humans, it's enabling it for software. Right? Software can become self-sovereign, which is a bit mad, but like this is kind of the basis of DAOs, right? Autonomous, clue is in the A. And I think it's very interesting when you combine this with AI, which is nothing to do with, quite the opposite of automation, right? AI is absolutely not about being autonomous. The exact opposite is about being reliant on an authority with a large access to GPU, right? With vast access to data, which you would assume is probably going to be private because they're going to want to outperform anyone else. And this is, it's the very opposite of these sort of open ideals that Web3 eschews. And it's there in order not to make things autonomous, quite the opposite. It's there to make devices intelligent in some questionable version of the word intelligent, but still more intelligent than they were before. And then when we combine automation and intelligence, I don't know if there are that many other properties, realistically, that we could exhibit in the digital world. Like from a digital perspective, we are intelligent, autonomous entities. That's kind of how you would characterize humans as opposed to like dogs or that tambourine, right? When we exhibit ourselves, when we manifest ourselves in the digital realm, we manifest ourselves as autonomous, intelligent beings. Well, it turns out that with these two technologies, AI and blockchain, machines can manifest themselves in exactly the same way as us. Imperceivably different, potentially. I mean, you know, there's the question of like the reverse Turing test, proof of personhood, in order to try to create some difference here. But we really have to try. Yeah? And if we don't succeed, and if we can't succeed, then there won't be a difference. Yeah, and I mean, there's a lot of sci-fi out there that sort of plays with this concept, right? But it's real now. Yeah, these two technologies have just made that real, and I don't know how obvious. You know, I think I did a tweet about it like in 2015 or something. It's like device, you know, AI is device intelligence, blockchain is device automation. Combine the two, you've got autonomous intelligence. And I'm not sure how much the practitioners of AI understand this. Because it becomes very dangerous. Like, they think of it as like, oh, well, don't worry, it's sitting behind OpenAI, and we'll make sure nothing bad happens. It's like, no, it doesn't work like that. It's like, once there is economic imperative for this intelligence to be used, as long as it can be used, it will be used. Yeah, they will cease to be the gatekeepers. And for that matter, they probably won't be able to tell the difference as to whether they're supplying intelligence services to humans or to autonomous software agents. So it's an interesting sort of side of the coin. that we're on. We're on the sort of, try to somehow make AI a little bit less, well, I don't know. Blockchain has two sides, right? On the one side, it's making AI more powerful than it otherwise would be, basically by allowing it to power software agents that are not in any way constrained by any sort of concept of human morality. Yeah. But on the other hand, it can also implement things like data provenance. We can implement things like first-person technology versions of proof of personhood, right? That avoid authorities but still deliver reasonable, credible proofs that the digital entity you're interacting with is indeed a unique person. And I think we need to be cognizant of when we're doing stuff in Web3 to understand, let's not make the bad side of this too bad without sort of also putting work on the good side of this, because it's kind of a scary world to live in if we're unable to tell the difference between essentially sort of bots, like online autonomous agents that are intelligent, and regular people. Like this is a very untested society, untested social change that at least personally kind of I find quite disquieting. Right, so Web3, Blockspace, main resource, I guess. Web3 isn't just about blockchain. There's, data publication. There's messaging. Neither of these things are particularly good to put on chain. I guess you could, but not ideal. And Web3 is about sort of having a sort of full spectrum solution for doing all the things that we could do before Web3, but using these resilient technologies. Blockspace is not a simple thing. There's not only like one type of block space, multiple ways of measuring block space, multiple qualities of block space. And unfortunately, lesser block space providers take pains to try to make all of this very opaque to users or potential purchasers. I don't think I need to say too much about this stuff. For what it's worth, a couple of other thoughts. I'm just going to flick through these and give thoughts. You can ask me more questions at the end if you want. So, we're talking earlier about potential use cases for JAM, now that, with JAM having such dramatically higher resources. I mean, even Polkadot has, really quite high resources, right? 42 compared to like 15, and Polkadot's not even a specialized storage provider. And I mean, JAM is like, wow, way higher, right? So it's kind of mad that, we've got, like, what is possible down here is just not in any way relevant to what is possible up here with JAM. Yeah? We're into categorical difference territory now. We'd have to think totally differently about what it is that we want to do with this. Now, of course, you can do the same things that you can do with this, but with this, and you can do it and scale it much, much more. But that's kind of not that interesting, because, well, for a start, scaling it requires to actually find the market, and that takes time to develop. But anyway, I just wanted to sort of get across, this graph is kind of quite helpful because, it's pretty obvious how much difference we're talking here. Orders of magnitude. This one is also interesting. Now this is, actually it's not this one, it's this one. This is interesting. So this was originally coming from a Cryptocarbon Ratings Institute. Okay. And obviously this is quite a lot lower than like all of this stuff. This is a proxy for, like, I mean, it's done as carbon emissions, right? Which is basically energy that it takes to run this thing, to process a transaction, I think. But because it's energy, it's also cost. Like basically the biggest cost to running this stuff is the energy that you have to put into the servers. I mean, you've got the capital expenditure as well, but it's relatively comparable, I would guess. The energy is probably substantially the biggest sort of difference in cost, and the multiplier is fairly substantial, right? JAM makes this even more cost effective because it reduces the number or increases the number of cores that you get per validator. Instead of getting, I think with Polkadot it's a fifth of a core per validator because there's 5 validators per cores. In Polkadot, in JAM it's a third. Right? And in essence, we're doing about 30 times as much work as we would otherwise have to do if the machine, if we were just running, paying for energy, paying for a program to run on a single machine. Now this is Ethereum's not on here, and I'm if we put the Ethereum sort of ZK thing on here, where everything, all Ethereum, all of L2, all the L2s, all of the native rollups are ZK proven with GPU supercomputers in really fast time, it's going to be really far up. Yeah, huge amounts of energy. And of course, if they've got the money and they don't mind pissing it away on this stuff, then it's fine. But the point is that this is a proxy for cost. So this ultimately, economically long-term speaking, this is what the minimum possible transaction fee would be proportional to on each of these systems. Yeah, like that's the marginal cost of a transaction, and the network might want to increase the transaction fee a little bit beyond that, so it makes some money. But still, that's the marginal cost, and it's way cheaper, way cheaper. And we get to feel good because it's got lower carbon footprint too. Okay, so building a Web3 cloud, how do we do it? Well, we want to get a nice fat kind of supercomputer, a nice fat computer that can process lots and lots of data, and then we want to have many of them, right? Potentially, when we run out of space on the first one, we want to be able to add a second and kind of connect it all in and make it very coherent. And to some extent, maybe it wasn't a sort of primary goal, but a sort of secondary goal of the JAM protocol was to be able to plug multiple JAM instances together into a sort of bigger grid. And I touched on that in my end of year write-up last December, but I don't want to go into it too much because it's still a little bit rough around the edges, but it is based on sensible sort of design direction that the foundation had in mind several years ago, even for Polkadot. Good, yeah. This you should already know. The 5 driving factors. Most important. Achieved with, more achieved with Ethereum. It's interesting, when we did Ethereum, we were like, oh, Ethereum, it's, I was always a little bit cautious about saying it's Turing complete. It's a Turing complete language, like the EVM is in principle Turing complete, right? You can write Turing complete programs with it. Ethereum itself, like the execution environment of Ethereum, is not Turing complete. You cannot evaluate Turing complete code on Ethereum. Why? Because you'll run out of gas. Yeah? The code that you can run on Ethereum has to run with a gas limit, and that gas limit has to be at no greater than the block gas limit. Yeah, so it's not actually Turing complete. It just has a Turing complete language that you can use to express programs in it. Compare that to CoreVM, and CoreVM is actually Turing complete. Like, not only does it have a Turing complete language, the PVM, it will just run the code until it halts. Yeah, and if it needs to pause until the next block, it will pause till the next block, but the code will just keep running. There's kind of a key difference. Coherency is a crucial one to cover of these driving factors, and it's something that I'll go into it in a second. I'll go into it now. Yeah. Okay. So I've done some little diagrams. I didn't cover these in the first talk, so I guess let's cover them in this talk. So problem with theorem 1, well, it's unscalable. So this is sort of like the state space. It's got a single state space, and this is sort of like the validators. It's got a single set of validators that validate that state space. And then you've got like some scaled up versions of ETH1, like EOS and Solana and so on. And they're bigger. It's got a bigger circle. This was my effort to draw Cosmos. So like basically lots of Ethereums with bridges between them. But the bridges go outside of the dotted line, so they're not secure. Or at least they're only secure on the weakest side of the bilateral. Plus, you've got different states. Yeah, so you're kind of siloing the parts of your ecosystem into different silos. The thing that I call persistent state partition. Ethereum with L2s, sort of the same thing going on, but kind of weird half thing with kind of got one validator set for Ethereum and another validator set for the L2s, and some of the L2s only have like 3 validators in their validator group, and it's trivial to censor, and then they use different staking tokens, and it's all a bit messy. And we still have this issue of persistent state partitioning between the different avenues that we go down. Polkadot. So kind of fix the whole security thing by putting everything under the same umbrella, more or less. But we've still got this persistent state partition. Different parachains. And this kind of brings us to that size synchrony antagonism. But I'm not going to go too deeply into this. It is I sort of discussed it a while back. 2 days ago. No, yesterday. And a while back. But this is the reason that all of these systems are doing that persistent partitioning, right? They have to find some workaround if they want to retain their speed and increase their size. There has to be some workaround, something has to give in terms of this coherency or this synchrony. I won't go into this too much because you've already seen it, most of you. But I will talk a little bit about what JAM sort of is. So JAM is generally coherent. It kind of stays mostly coherent, but it has some elements of it incoherence. That happens over basically every 6 seconds it kind of loses coherence, and then at the end of it kind of gains coherence again. It kind of snaps back in. As opposed to other systems that will tend to kind of vertically partition their coherence. So they basically say one parachain or one L2 or one blockchain, well that's just going to be always coherent with itself, but never coherent with anything else. And JAM sort of rotates that and says, well, actually, we're going to keep all of these sort of parallelized compute bits, cores, stateless, but we're going to keep the system quite coherent. We're going to make sure it ends up being totally coherent every 6 seconds. With JAM, we also introduced this dynamic, this distributed data lake, and a very big one, 1.6 petabytes. That's very big for blockchain anyway. And again, with every 6 seconds, this synchronizing. So, or the system sees the same data lake, but 6 seconds later. and 4 kilobyte segments that are placed into all the data placed into the data lake is done in 4 kilobyte segments. I mean, actually, it's slightly over. It's 4,104 bytes, but that doesn't really matter. And so, in terms of Ethereum, if you ever want to have this conversation under that dialect, then in some sense we have, again, quote unquote Turing complete. It's not really Turing complete. You're still limited by this gas limit, right? It's a lot bigger than it is in Ethereum, and even quite a lot bigger than it is in Polkadot, about 2 or 3 times bigger than Polkadot. But still, it's not actually Turing complete. It has to pack up at the end of this thing. It has to complete the computation, or don't know. Yeah, throw everything away by the end of this period, and they're stateless, with the slight exception that it's got access to this data lake, and then one kind of smart contract chain that can fold all of this into a coherent state. So this is sort of, I've called this like a roll-up reactor before, because there's like kind of roll-ups that happen on here, and then this kind of reacts their outputs together as a crucible into a sort of single coherent state. And this is the, short list of technologies that we've used to achieve this. So the cynical roll-ups, also known as ELVs. This is what gives us our security. Something I haven't written here is the erasure coding system, which is relatively, not uncontroversial. It can't really claim it as a JAM technology. It's just pretty standard, but still, we make substantial use of it. Safrole, which is a new ZK-based block authoring system that prevents or makes it very difficult to know who the next block is going to be coming from. Grandpa, which we already use in Polkadot for finality. It's an adaptive finality gadget. And then PVM, which gives us this very whizzy fast continuations friendly instruction set. If you're wondering, PVM, bit of a deeper dive. So it's based on RISC-V, if that's not already obvious to the world by now. RISC-V code, it's different to PVM, but it kind of gets recompiled into PVM. 13 64-bit registers, pretty standard memory address space. Not a von Neumann architecture, it's Harvard, but it doesn't really come into it that much. Recompilation is fast and relatively, doable. If we're publishing Jan's talk where he explained a lot of this stuff. So if you're wondering, then keep your eyes on the website, I guess. Can be metered with, we hope, quite low overhead. The metering itself will be low overhead. The gas costs that the metering implies may not, we'll see exactly what the ratio is to the time that it takes for those for that gas to be sort of spent. We don't necessarily expect a perfectly optimal gas per time ratio, but we'll see. Continuations are crucial for things like CoreVM and running Doom. And yeah, we've demonstrated that this thing can go very, very quickly, especially in comparison to other industry virtual machines. So yeah, JAM has services, not smart contracts, but they are a bit like smart contracts, but they're very much more asynchronous. And they have a few different entry points: refine, accumulate, on transfer. The refine entry point is stateless apart from the data lake, whereas the accumulation entry point is fully stateful, but you get much, much less gas and bandwidth. So you kind of have to work out how to split your smart contract logic between these two, and that's the trick with making services. Making an effective service. You don't get the sort of laziness or implied laziness that you would on a regular smart contract platform of just basically sticking all your logic in one place. That said, you don't get that laziness anyway, really, because the constraints placed upon you on your logic in that one place are so incredibly high. But still, in JAM, you have to make this additional design call. JAM also, very importantly, implies a bulk purchase of Blockspace, of CoreTime. This is very different to typical smart contract platforms, where the users will purchase gas when they want to use the system, when they want to send a transaction. In JAM's case, it's more like the application purchases, cores, or large amounts of block space or core time, and then figures out how to use that block time for its users. Much more similar to the Web 2 model, right? And actually quite similar to the Polkadot model. JAM is totally permissionless. There's no no limits to how it can be used, really. And it's agnostic to all of this stuff. Like, it's designed to be a protocol, not to be specifically a network. Yeah, it's a general protocol. And to some extent, there's like an invitation for other networks to take a look at it, right? Maybe they also want to sort of use it. Right, I'm not going to go too deeply into this. I think it's probably just too sort of technical, and it doesn't matter that much. And also, time's getting on. I do want to talk a little bit about CoreVM, because kind of cool, kind of fun, and I've got a bit of a demo. So CoreVM, what's the why? Well, it's like developing on a blockchain is kind of not so fun, not so good. You have a lot of strange stuff that you have to cope with, and the constraints can really, I would say, sort of prejudice the path that you take and prejudice the sort of software that you'll write. And CoreVM is here to sort of demonstrate that it's possible to use, to build resilient systems, build Web3 systems that that look or that have platforms that look a lot like Web 2 platforms, that look much more like Web 2 platforms and Web 2 technologies and regular technologies than they do like what's come before in Web 3. In that sense, it's more of a sort of statement piece than something that's necessarily designed to be used in production. But that said, Ethereum was kind of the same thing, and people still haven't stopped people using that for sort of production usage. So you can think of it as Docker for JAM. Yeah, it gives you an environment that's like a sort of regular computer. It's very standardized, and it's totally isolated from everything else. Yet it still has very high speed that's comparable to, what a laptop would go at, or at least what a core of a laptop would go at. RISC-V compatible, so it's compatible with a lot of tooling. Page memory, so memory just looks regular. Continuous execution, so you don't have to worry about block gas limits and so forth. And message passing between different instances. All right, good. Right, let me see if I can make this demo work for you. So I started a testnet. It's just been pootling along while I've been doing that talk. There it is at the bottom. I probably can't see that, can you? Let me move it across for you. There you go. So that's just the thing from the testnet. It's got 6 nodes, and they've got different colors, so you can kind of see it's making blocks and not doing all that much other than that. Now I have this program, JAM top, right? Table of processes. You might be familiar with the Unix version of top. Let me put it on for you. There it is. That's just like telling me what I've got going on my laptop right now, yeah? So a bunch of processes, and it's got like a CPU percentage for each one, and CPU usage up there. Well, that's it for JAM, right? Because JAM is a computer, right? That's the M machine. It's a computer machine, yeah? Join accumulate machine. But the M implies it's a type of computer. It's just a decentralized computer. In reality, blockchains are decentralized computers, but they're not very easy to recognize because they're so fixated on transactions. Yeah? And they're so they have such weird execution environments and languages and restrictions and constraints and assumptions and prejudices that it doesn't really make sense to put this sort of thing for like Ethereum, right? It's too weird, it's too niche, it's too not like a regular computer. But it turns out JAM is quite a lot more like a regular computer than basically anything that's come before in blockchain, to the point that it actually makes a lot of sense to have this tool so you can see what's going on the JAM computer. Now this JAM computer is a small JAM computer. It's a testnet that's just running on my laptop. So it's 6 validator nodes, 2 cores. It's the tiny configuration if you're familiar with that. So you can see up there, it has 4 graphs, right? 0, 1, A, and X. 0 is core 0, 1 is core 1, A is the accumulation core. Actually, A and X are both the accumulation core. A is for accumulation, X is for inter-service transfers, which also need to be processed on that same core. So those are basically the sort of 4 things, 4 kind of CPUs, if you like, that JAM has. In fact, actually 3 CPUs that JAM has. And these are the different processes that are running on it. Now, they're not called processes of the JAM, they're called services. But they're still just basically processes. They're just processes on a decentralized computer, that's all. Yeah? And then we also have the storage, right? Like kind of the hard disk. And on here you'll see, you know, I don't know, where have we, like, somewhere in here it will tell me the hard disk, like disks, there you go. Read, written, blah, blah, blah. Well, we've got a hard disk as well. It's not called a hard disk, it's called a data lake, but it's the same thing, it's persistent storage. And we put things in exports, and we take things out, that's imports. And we have data I/O, that's the extrinsics. Yeah, we have the same thing going on. It is just a computer, it's just a decentralized computer. All right, so let's do something with a decentralized computer. Now we have a sort of thing here. What it's going to do is it's going to create a service, a CoreVM service. So basically a Docker container, if you like. And inside of that Docker container, it's going to put a pre-built version of Doom, right? So let's do that. It's going to build a little bit of code first. Now when it does this, it should, if it's working, we should see a service pop up here. And it'll initially not know what it is because it won't have uploaded the service code yet. There we go. So that bootstrap service, that's a sort of, as you might imagine, that's the bootstrap service, right? That's the service that allows us to load other services. Yeah. So we're loading a CoreVM service, and there we go. That's just loaded in. Yeah. We've started CoreVM. That's a CoreVM process now that's running. And you can see on the graphs there, it used a little bit of core 0 and a little bit of the accumulation processor, yeah, to do that. And now we have 2. It's not doing anything yet. It's just sort of sat there, idle. To make it, it will actually start doing something, but we want to see what's going to, you know, this process. We want to kind of plug ourselves into its output, and it's got a graphical output, right? And we have a graphical sort of monitor, remote monitor for it that lets us actually open up or view its graphical output, its video output. We just have to put the thing in there, the service ID, and we'll be able to see it. So this is its graphical output now as it's running. And there we go. Now, as you see, CoreVM is now at the top of the list because it's constantly, you know, churning through compute, right? It's running on a core of the JAM, of this computer, this decentralized computer. And you can see it's got
It's taking up 5% of the refined core and 3.5% of the accumulation core. And we've actually got it switching between core 0 and core 1, just to sort of demonstrate. It doesn't necessarily have to sit on one core, right? Every block is going to switch to a different core, and it's still fine. And we can see at the top, we've got our AP, or accumulation processor, that's running at 1.8%, and our cores that are running at, what, 5.2%. That's how much it takes to execute Doom, right? 5% of a core. So, you know, can execute something, I don't know, about 20 times more complicated than Doom, and it'll still only use one core. JAM has 341 cores. We can see how much gas is being processed. One refine took 80 million gas. That's how much it takes to generate 6 seconds worth of Doom output. And one in the accumulation, it uses 365,000 gas, so a lot less gas. So all it's really doing is checking some hashes and updating some memory memory items, basically, making sure that refine isn't lying to it when it comes into some future when it processes the next 6 seconds. And that's it, really. Now we can. I want to emphasize that, like, it's a computer. I can use it for other things, right? It's got 2 cores, so, you know, it multitasks. So let's do something else with it while Doom is running. So we have this tool, JAM tool, right? The first thing we're going to do with the JAM tool, let's just create a service. Going to create a demo service. So we have this pre-compiled demo service. It's just the thing I use for demos, and it's sending it in. And now, if you look, JAM Bootstrap service is refining. Now it's accumulating. We've got a new service. That service is going to have its metadata provided, its code provided, and then bam, it's updated. That is the demo service. I can send messages to the demo service. I can kind of kick it off running with some information, and it will run, right? But I'm not going to do that. I'm going to create another service. I'm going to create the benchmarking service. Benchmarking service is another service coded that just uses as much CPU as possible. Like, makes a point of just using up lots and lots of a core. And bam, there it goes. It's initializing now. It takes a block. Basically, you create it in one block, and then you have to sort of push its code in the next block. There we go. It's done. Now, to make these services do something, you have to sort of send them some information, give them a work package. So let's give it a work package. I'll need to tell it what the service is. So it's bench service. It's this ID. So I'll just copy that, put it in here. And what we should see is just a massive yellow blob as the bench service, there we go, uses all of the core at that point. Yeah. Of course, JAM doesn't stop because JAM's, you know, on a different core, and that's fine. Yeah. We can keep doing this if we want. At some point, we're using like just the PVM interpreter while it's on the OS, macOS, because the ARM recompiler isn't finished yet. But if this were on a PC, I wouldn't have to, you know, I could do this just indefinitely, and it'd be a big long yellow blob going along there, and it would be fine. On this, it might start, you know, taking too long to make the work packages because it's just one laptop and it's running 2 JAM cores in interpreter mode. But I don't know. I haven't tried it yet, so can't say for sure. Anyway. Yeah, hopefully that's given you some idea as to what it is that we're sort of doing with CoreVM. I'll leave that playing in the background, and I'll just continue a little bit further into this presentation. So what's happening there? So we have Doom sitting inside of this Docker container, CoreVM, Docker container for JAM, right? Sits inside, and then we have a sequencer. In fact, it's kind of like a simulator. What it does is it works out which memory pages Doom is going to need to produce the next 6 seconds, and it just makes a work package that sort of tells it what those memory pages are. Yeah, it needs to know in advance, because if it doesn't, there's no way that once it's in here, it could feasibly tell the validators, oh, actually, I need this memory segment fetching from the data lake now. It would just take them too long to do that, right? The latency would just go up and up and up, because it takes, I don't know, maybe 200 milliseconds, 500 milliseconds, something like that, to reconstruct a memory segment. Yeah. So you can't reconstruct 400 memory segments unless you know what the 400 are ahead of time. If you know them ahead of time, you just send off for all 400 at once, reconstruct them all at once, and it's fine. But if you're doing it like one at a time, because you're like waiting until there's a memory fault, and it's not going to work. So that's why we need the sequencer then there. There are other potential ways of sequencing. You could guess what the memory pages are, and if the application tends only to use the same memory pages 99.9% of the time, and you probably do that, and you'd have a much simpler sequence, so you wouldn't need to simulate the program to work out what the memory pages are necessarily. But we do it the proper way, so that it will work with any software. When it's inside of Docker, of the CoreVM thing, what's actually happening? Basically, we have the distributed data lake, right? So we have a vast amount, this 1.6 petabyte data lake. And what we're doing is we're pulling in the old RAM that we're going to read, right? Not pulling in all of the old RAM. That could be too big. Yeah, that could be, hundreds and hundreds of megabytes. Could be even more, right? We don't know. We don't put a limit on it. It's a 4 gigabyte 32-bit memory thing, right? So it's like it could theoretically, I suppose, use all of the memory. I mean, that'd be a bit mad, but in any case, we're only going to fetch the bit of memory that it's going to need to do the next 6 seconds of computation. And we do that. We pull that in from the data lake. We let it do the next 6 seconds of computation, and when it's finished, all of the pages that have been touched, and any page that is new, we push that into the data lake for the next 6 seconds. Yeah? This all happens behind the scene. This is all happening by CoreVM, not by Doom. In addition to pushing these changed memory pages out, we also push out video frames and audio frames and console frames and any other data that we might want to expose to the external world from within JAM. That also goes into the DA. And then once we've done that, we make sure that we have an address for these frames. So we basically index the frames along with their kind of DA address, and we put that somewhere where it can be easily found, somewhere on chain. We then have a totally separate executable, which I started at the beginning, right? This viewer thing. And it's the viewer, it has no knowledge of what's going on with Doom, right? All it knows is there's a CoreVM instance on chain, and it's just looking for these references, these addresses into the DA for the frames and the timestamp. And it's just fetching those from the DA and putting them in the window and animating them according to the timestamp. So that's what's going on. That's what you just saw. Yeah. So what is it that we want to achieve with CoreVM? I mean, at the moment we have the video output driver. That's why you could see what was going on in the computer, what the monitor. If you imagine it was a real computer and you plugged in a monitor into it, that's what you would see on the monitor. Yeah. So we had a kind of graphics driver, yeah, for Doom, like for the Doom executable environment. And we had a sort of an executable that was basically a software monitor, yeah, software video monitor. Well, we'll probably want a software audio monitor as well, and an audio, a virtual decentralized audio card that goes along with it. Same for the terminal output. Yeah. And then some other more esoteric things, fixed storage, so we can have like a read-only file system or read-only memory. Keyboard input, probably some other kind of form of input. Although obviously programs are pretty software, regular software is kind of used to the concept of a keyboard. It's not like used to the concept of a transaction. So there's going to be some sort of imagination that's going to have to go on here to see what we can do to combine these two paradigms. And then a few other things, LAN and so on. So that's where we want to take CoreVM. And then CorePlay is basically CoreVM, but with a very agile, decentralized co-sequencing service that makes sure that the different CoreVM instances, if you like, that want to interact with each other atomically are co-scheduled and know they're co-scheduled and therefore can have atomic interactions. Yeah? And that these atomic interactions are checked all the way down at the end of the accumulation stage. So it's not possible for one to believe it had an atomic interaction, but the other not to believe it had an atomic interaction. It's crucial that if it's an atomic interaction, either it happened or it didn't happen. It can't have happened for one, but not for the other. So this needs to be checked securely as part of the accumulation pipeline. You can think of that as a smart contract operating system for JAM. Doing it this way basically gives us a smart and it's better than smart contracts, right? Smart contracts are highly transactive, which means they have gas limits. They have to do a transaction and then they stop doing the transaction, and that has to happen within a block. You have to be sort of done with the transaction by the end of the block. We can make it so that you don't have to be done with the transaction in a block. You just saw Doom operating. Well, imagine Doom, or imagine the flexibility of having the ability to execute Doom, but it's a smart contract. It's like a smart contract that can just execute indefinitely. And if it wants to take more than a block to process a transaction, that's totally fine. If it wants to halt halfway through a transaction and then process a bunch of other transactions and then continue on that first transaction at some later stage, also totally fine, right? You can just have totally different attitude when we're coding these things. So it's much more kind of like an actor. But the nice thing is it's not entirely like an actor either. Actors are asynchronous, they only compose asynchronously. In principle, we can make our actors compose synchronously. We can have them actually call into other actors and get a result within a block, like instantly. The whole system becomes elastically scalable across cores. So we can, if we have more and more actors doing more and more stuff with each other, that's fine. We just add more and more cores and it kind of just scales out. I mean, eventually we'll run out of cores on the JAM instance, right? I have 341, that's a lot, but still, if it's, if people are using it a lot, it will run out. And then we have to think about introducing more JAM instances. But again, JAM is partially designed with that in mind. And then we end up with this sort of system where we can achieve global atomicity. Like, not everything can atomically compose with everything else at the same time, obviously, but in pockets, we can achieve this. Yeah? In core size pockets, we can achieve it. Good. And how do we do it? Well, it's basically, it's not really a new technology. It's just co-sequencing, co-scheduling, but we're just keeping everything small, lightweight, yeah? Which makes the whole thing a lot more viable and a lot more scalable. There are still, problems to be solved. There's still a lot of design space to explore, particularly in keeping things decentralized and censorship free. And we have some ideas, but it will take, it's not going to be developed tomorrow or anything. This is like a long-term plan. But the first half of this plan is JAM, and that's thankfully getting to a stage where we're approaching, I think, maturity. Good. All right. And very quickly, why not zero-knowledge proofs for scaling? Because they are expensive. For doing serious scaling, for doing the sorts of processing that we want to achieve with JAM, we're looking at like a 2 million X. That graph from before, as I said. Like Polkadot was down here, Solana was up here, that's the cost. If you introduce ZK proofs into that, it's going to multiply it up a lot. And that's not what we want our costs to be low, because our costs are the marginal price, right? Our costs basically limit how little we can charge for using this computer, and we want to charge almost nothing. I mean, we ideally would charge nothing, yeah? Free computer for everyone in the world, that would be ideal. That would be difficult to achieve, But we really want to keep it down, yeah? And paying 2 million X more for correctness does not help us keep that cost down. Good. Thank you for your attention. Sure, yeah.
Okay, I think we can have some questions. I think it's the right moment to ask a question.
I'm going to have a stool.
Are the mics around? Do you see any mic anywhere? We're going to find out. Question?
Yeah, thank you. I saw you talking about the role of sequencing and then also talking about the design space for keeping things decentralized. Is that one of the places you're looking into, like decentralized sequencing for CorePlay?
Yeah, I don't think CorePlay is going to be that, CorePlay shouldn't be centralized. Yeah. That's kind of important. Now, of course, there's...
It's quite interesting to decentralize sequencing.
Yeah, there's inevitably going to be a trade-off here. And at the moment, my expectation is that, while CorePlay won't be centralized, there'll be many different participants in the sequencing process, there will likely be a rotating leader that hands out portions of the actor space to be sequenced, right? That seems to me to be the most obvious way of kind of squaring the circle and having still relatively high performance, but still avoiding censorship. And the reason that we want to do this isn't for correctness, right? Correctness will be checked at in JAM. The reason that we want to do this is to avoid censorship and avoid potentially just malfunctioning malfunctioning builders from just not doing anything. And this should achieve both of those goals. I mean, maybe not perfectly, theoretically something could be censored for a block or two, but again, it comes at it's like, where's the trade-off? But the nice thing with the CorePlay concept is that you don't need to just have one set of sequencing participants. You could, in theory, and in practice, have several different sets, each hitting a different trade-off for censorship versus performance. And it might be that you just always choose the high performance one until you run into a censorship issue, and then you switch to another set that are much more about censorship resistance.
Totally. Cool. Thank you.
Hi, Gavin.
Hey.
I'm just wondering, what would stop a foreign actor to use the entire network, let's say, to train a massive AI, for example?
Probably, training AI is really GPU work. And while JAM is very, very performant for blockchain standards, it's still very much CPU, a sort of CPU type of processing. I mean, there's nothing, so nothing is the answer, except for the fact that, JAM wouldn't be high enough performance to come anywhere close to what you would get if you had probably even just, I don't know, somewhere between 1 and 5 high performance GPUs. That's probably the area where JAM is at. 341 AMD Threadripper, 5 gigahertz running at, say, around 40% of their performance. That's kind of, no, not even that, probably more like 25, 30% of their performance. That's where we're at. So what's that? About 80-ish cores. So it's, 80 Threadripper cores, at full speed. I mean, it's good for blockchain. It's not going to be able to train much of an AI anytime soon. And I mean, AI also, I think, is it's about floating point weights, and JAM doesn't have, or the PVM doesn't have floating point support at this point. Might be something that we consider later, I guess, but at the moment it's integer only.
So the next project is JAM graphic card.
Actually, it's kind of, yeah, there's nothing stopping us from adding, I mean, at the moment we have refine and accumulate, right? And refine is CPU stateless with access to the data lake. Accumulate is CPU stateful access to the chain state. There's nothing stopping us from adding a third computation phase. So when refine happens, you could also have a GPU refine, right? And the two could go off together and come back 5 seconds later, and you've got the GPU output and the CPU output. Like, that's totally viable. The only thing that would be caution is that you have to add GPU requirements to the validators, which I'm not sure if, I mean, that's going to increase the cost for running a validator, capital cost at least, probably the energy cost quite a bit too. But yeah, I mean, there's absolutely nothing stopping it other than a bit of having to update the grey paper and code and all the rest of it. If it turns out that it's something that, you know, makes a big difference, then it's definitely something that you can consider adding.
Hey, I'm sorry, that was super loud. So it's not necessarily a general-related question, but for you as like a Web3 thinker in general, so what I see currently is a big threat for a future Web3, for a future based on the Web3, is the fact that all our infrastructure is still based on the Web2. So we have like super centralized several internet service providers that can, you know, do the deep packet inspection and pretty much block all the blockchain, all the Web3 future in a second. So like, my question is, have you ever thought about it? Do you have any like ideas or maybe projects interested to follow, to think about?
I mean, yeah, it's a big elephant in the room, really. And for sure, there are lots of ways around this. One of them is just go really hardcore mesh networking, right? And have people provide their own internet. Another, if you have to go via sort of untrustworthy internet providers that might be censoring you, then you have to start thinking about, what's the word? Sort of masking your packets, right? Disguising them as other things. Forget what the word is now. There's a cryptographic term for this. And I think to some extent this already happens a little bit with VPNs. Like some VPN services will do cunning obscuration of VPN traffic, so they'll kind of hide it as HTTP, HTML, and like use those ports and try to even maybe change the data so it looks like this stuff. There's also, you know, this is something that we're also doing in Polkadot. It's like mixed nets, so trying to again obscure traffic and mix in different types of traffic so that maybe more sensitive traffic is obscured as part of less sensitive traffic. But yeah, I mean, it's a lot to do. It's a big problem. And I mean, one of the very easy ways that we need to address this is just by using, you know, non-centralized services, like not using websites, not using RPCs. Like, you know, if you're particularly in the Ethereum ecosystem, this is super prevalent, and it's like, oh yeah, the base network might be quite decentralized. I mean, arguably, but you know, using any of the services on it, and you know, it's like, oh well, you got to go through a centralized website, and you got to go into a centralized RPC provider, and it's like, well, you may as well just be using a centralized service, especially when that service, the team behind it, is in a regular company situated in a regular country, and it's like, well, what exactly are you getting out of putting it on chain? You know? So yeah, I think this is not this is not a problem that is limited to any particular ecosystem. I think some ecosystems have a greater desire to solve it than others. I think some are just don't care, shrug their shoulders, sure. I mean, we're a foundation. We run our own RPCs. We run our own website. We promote the services that run on it. Like, it's like, okay, well, you know, you are just basically, you know, Facebook. Others care a lot more. But we need to be very, very careful to ensure that light clients are first-class citizens. That I would say is probably the first thing that the first problem we ought to solve. Like light clients, first-class citizens, and then secondly, sensible decentralized storage and access for the website, for the front end, right? I think with those two things, we're already, you know, halfway to sensible resilience. Like the next half is going to be a lot harder, right? ISP resilience, a lot harder. But ISPs generally don't have their shit together enough to, you know, do this kind of packet, you know, inspection and trying to. I mean, maybe some countries, but and maybe that will change in the future. But I think for now, these are the two things I would worry about. And I mean, it's a lot harder to block P2P traffic than it is, especially disguised P2P traffic, than to block an RPC or block a website, right? This is super easy.
Just another high-level question. I was wondering, it might have been crazy to ask a few weeks ago, but how resilient is JAM to nationwide power cuts?
Well, it depends where people end up hosting the JAM validators. If they're all hosted in Spain, then it might be an issue. But no, I mean, I think with the validators of Polkadot, I think we've seen like fairly decent spread across the globe. I think it's like they're on all 5 continents, I think. I mean, not Antarctica. 4, 5, North, South America. 6 main continents. And yeah, the network should function relatively fine, even with only 2/3 of the validators, assuming that those ones that are remaining are all honest. One thing that I would like to see in this direction, though, is geographical incentivization of geographical decentralization. So one way that we could achieve this is by, I mean, you've got the IP address that you can kind of analyze and say, right, the validator gets paid more if the IP address is in a particular geographical region that is underrepresented. This is like a little bit, this could work, but it could also just be spoofable with like VPNs or whatever. Now, whether you'd want to spoof using a VPN, given that you probably are going to need at least 500 megabits up and down, that might not be such a good idea, and you might end up screwing yourself. So this might be a viable way. Another possible way of doing it is also to have proof of personhood record which geographical region a person has proven themselves in, say for 6 months running, and at that point, if that person sort of has a validator, or validators have to be associated with such a person, and then have the people be geographically distributed. I'm not sure which one would work better in practice, but I think it is probably something that we may want to sort of consider when the more pressing work is finished.
Thank you.
Okay. Hello, my name is Antonio. I work at Swarm. My question goes towards the data lake that you put over there in the presentation. I'm just wondering how resilient to censorship is that data lake? How about possible deniability of the nodes? In essence, how resilient it is to third-party attacks to that? Because I'm thinking on limit or extreme, not extreme, but limit use cases where there might be some people who wants to So how is it solved?
So we use erasure coding. So all of that 1.6 petabytes is erasure coded at a 3x rate across 1,023 validators that are pretty hefty machines, right, with pretty hefty uplinks. If you wanted to censor someone from getting data out of the data lake, and it would be basically impossible to censor someone getting data into it, because you just send your data into the validator directly, and then they would distribute it to, they would erasure code it and distribute it to other validators. And that would just be on a quick peer-to-peer basis, so you couldn't really prevent that. You could attempt to DOS the network, but you would need to DOS 2/3 plus 1 of the nodes. That's a lot of DOSing, and I don't think it would be too long before the nodes basically just blacklisted all the IPs that were trying to take them out. It's intended to be highly resilient, right? It's intended to be as resilient as the network itself, right? It's a first-class citizen. Now, I don't see it as being an alternative to decentralized, long-term decentralized storage, or like kind of more general systems for decentralized storage, because after 28 days, it gets ejected from the data lake. The data lake is here for transient working data, right? Longish, like medium term, 28 days, short to medium term. But if you want the data to be around for more than 28 days, you either have to reinsert it, which can become quite costly. You've got a market for that. And of course, you need to schedule it and all the rest of it. Or you need to store it somewhere else, right? In another service that will store it continuously. And then ideally a service that you can fetch it out again from at some later stage. So it fulfills a slightly different trade-off between permanence and security.
Thank you.
My question also about data lake. So this 1.6 petabytes, if you said that erasure coding is redundant X3,
yep,
which is, my calculation says that it's like around 3 terabytes per validator would need to be of a data, right?
yep.
But is this 1.6 petabytes set in stone, or I assume we can like in future scale it to, like as soon as like hard drives became cheaper, right? And like Nakamoto indexes not suffering, we can like scale it to the space.
Yeah, I'm not like a zealot or anything. I wouldn't like say that whatever the constants are in version 1 of the grey paper, that must be what they will always be forever on all JAM networks. No, absolutely. These constants can change and can be updated. The constants as they are computed based on a model. So I've modeled all of the bandwidth costs for each of the subsystems. And these are the numbers that I came up that basically pushed it to about half a gigabit. On the assumption that it would be we'd have about half a gigabit of bandwidth for every validator across to every other validator, like not every other validator, but between all of the communications channels to all of the other validators. The other half gigabit of bandwidth we assume is either lost due to inefficiency, practical aspects of internet uplinks, or being used to give data out to nodes other than the validator nodes, right? At the end of the day, it's only the validators that certainly have access to the data lake. So any other nodes that might want access to the data lake would need to go to a validator, and that data would have to be sent over using the validator's uplink bandwidth, which realistically, I suspect what we're going to see is maybe not in version 1, but validators being required to keep a kind of side node where all of their DA fragments get sent to, get kind of duplicated onto, and then that side node would be basically how nodes outside of the validator network get data lake data. Because getting it directly from the validator is not going to scale. Yeah. So, but yet we want to kind of get that data out onto some distributed file, like distributed data service system like IPFS or something, something kind of like on the IPFS network, so it can be very easily replicated and distributed. Having the validator sit on IPFS probably isn't that sensible, so we probably want to have the validator have at least one kind of side node that that data gets replicated onto, and from that node out into IPFS or wherever.
And then to follow up on this, so with the PVM, we can like benchmark and measure the gas cost for the execution. But I'm wondering about the storage. Have you done any like modulations about the fact that like people can just like store a lot of data, like full of this like 1 and 6 petabytes without actually doing any executions? My question is like the execution benchmarking is happening on the PVM, right? This is where we like can charge person for like doing execution, but for storing actual data, I assume it's not like it's not something you can benchmark with PVM. This is something should be like on JAM OS or like.
So yeah, PVM is indeed benchmarked in terms of execution time. And yes, storage is a different resource. So with storage, we have essentially for every work package, which is 6 seconds worth of use of one core, we have 12 megabytes that can be introduced into the core and 12 megabytes that can be yielded from the core. Additionally, 48 kilobytes that can be yielded from the core into the chain logic. So those are the big arrows basically. And yeah, you could totally use the 12 megabytes just as DA, just as sticking stuff in the DA for 28 days and not do anything on the core at all. We don't prevent that. That would be wasteful. Like PVM's just going to sit not doing anything. And in principle, if you can find a job that just needs to use the PVM but doesn't need much data, you could essentially make a work package that contained both of these jobs. And one of them is just sort of putting data into the data availability system, the data lake, and the other one is taking a little bit of data and doing a lot of compute on it and feeding it into maybe onto the chain or something.
But as the idea, this is wasteful for us, but this is actually the attack vector for the.
Oh no, I mean it's wasteful for them, right? There's still a limit. So that even if all 341 cores had 12 megabytes of data being uploaded into the data lake from using those cores, and the cores were running the benchmarking program and running maximum PVM, and all the chain, where you're running maximum PVM on the chain, and doing all of maximum I/O into the chain state database, it should still work fine. We're going to test this, right, using the toaster, but that's the assumption based on the modeling that these numbers will give.
And it will take a lot of time to upload all this 12 megabytes, 1 and 6 petabytes.
Yeah, we'll see. I mean, 28 days, I guess. Yeah, but I mean, yeah, you don't need all 28 days. I mean, these SSDs, you know, they give you very particular read-write characteristics. So we probably don't need to literally fill up 4 terabytes of SSD to test whether the data lake works properly. We'll probably do that quite early.
Excuse me if my question is a noob one, I'm not a programmer, but somewhere in your talk you said that governance is not the main scope of JAM, and afterwards you showed you were working on something like virtual driver, graphic virtual driver, you're heading towards audio, etc. And also that zero knowledge proofs is not correct, is not a good algorithm, sort of, cryptography for the JAM. And you also said that even AI is not the best use case for what you're building. So my question, I guess, is how do you see, because I work with online voting, with homomorphic encryption, zero knowledge proofs. Would you recommend me to use JAM for this particular use case? Or is it something not on the radar, or how do you?
So I'll clarify what I meant by ZK not being sensible in this context. It's not sensible for scaling correctness. All right? In JAM's case. Why not? Because JAM seeks to be a general purpose computation system. And ZK doesn't work very well scaling general purpose correctness. right? If you have very, very niche and oftentimes linear math correctness problems that you need to scale, it might work quite well. But if you want to do like bit manipulation correctness, and a lot of it, it doesn't scale well at all. It ends up being extremely costly. Now, that is definitely not to say that you can't use JAM to do ZK verification. It's really good at this, right? And indeed, one of our existing sort of ideas that we'll probably put into start development on very soon will be a ZK-based transaction processor system on JAM. And it will totally use ZK. Say again? Good, yeah. It will totally use ZK to do this because it's a great solution, right? It basically, JAM's actual, one of its biggest problems isn't compute, right? Its biggest problem is bandwidth. And it's got a lot of bandwidth. But if we want to use that bandwidth for at least some of the jobs that we sort of have an idea about, we're going to, we're not going to end up using very much of the compute. I mean, I showed you the Doom demo, right? That's 5% of a core that it uses. It uses all of the core's exports, right? It uses, if you looked at the, I don't know if you noticed, you probably didn't notice, but anyway, the export count was at 3,000. That's about the maximum that a core can export, 3,000 4K segments. The imports were quite low, and the CPU usage was like 5%. So actually, it's the bandwidth that is going to be our bottleneck, right? And the thing about ZK is you can, to some extent, switch or you swap out or trade off bandwidth for CPU, right? You can basically kind of make a ZK proof and reduce, depending on exactly what it is that you're proving. There's a lot of like factors here, but to some extent, reduce, often, sometimes significantly so, the amount of bandwidth that you need for that correctness. And JAM can totally use this. But if we wish to achieve what we achieve with JAM itself using ZK, it would be very different. Instead of, say, elves, instead of cynical rollups, it would be very, very costly. And that's really what I mean here. And to take your point of governance, it's not that you shouldn't do governance on JAM. You absolutely should do governance on JAM, and indeed we will do governance on JAM. When Polkadot uses JAM, it will still be Polkadot governance. It will just use JAM to, compute it all, do all the correctness, store everything. It's just that the JAM protocol is agnostic to governance. It doesn't care. Right? You can do what you want on JAM, right? It's just a computer. Doesn't mind whether you play games or run spreadsheets or whatever. And on the last point, yes, you totally should use JAM to do your homomorphic ZK voting system.
Any
All
more
right.
questions?
So I was wondering if you could reflect on the 2021 era way of selling cores, if you could call it that. At that time, if we all remember, I don't know who was around then, there was an auction for just a few, maybe 5 cores, if you want to call it, because they sort of do what the cores are going to do with core chains, I imagine, in the near future. At that time, Polkadot was the monopolist. It was the only place you could get roll-ups, really practically speaking. There was some, if you want to call it that. And now you are in the short-term future when we go from 60 or whatever the number is now in Polkadot to 341. You're basically flooding the system with 200. So do you think some of the scarcity that was there in the let's pull them out, put them out 5 at a time or something like that should be adopted in whenever we get around to that point in a year or two, or should we stick with the kind of like let's let the market decide for everything with the kind of flooding system? Why the change?
So it's an interesting proposition, and I think it's not one that I would want to make a call on particularly. I think Polkadot governance could reasonably make the call to disable some of these cores if that's what it believed was in its interests. I am much more sanguine about just like, we have this, let's use it, even if it means, kind of cannibalizing to some extent our market.
But you know, at the end of the day, it's Polkadot governance that decides, not me. Or it should be, anyway. The reason that I'm more sanguine, I think there is a sort of rationale here, is that we're not, like, if you limit the cores, it assumes that you kind of got a monopoly. It assumes that people will come and use these things even if the price is high. Yeah, and this then comes with a presumption that other ecosystems cannot provide the same service or better, maybe better connected or something, I don't know, but with the same or lower price. Yeah, and this seems presumptuous to me. I think it's a much safer bet to basically outcompete the competitors in terms of volume and allow for use cases, because we have such high volume and low price, that wouldn't otherwise be possible. Kind of you heard of Ryanair, EasyJet, right? You heard of these airlines, right? That's what they did. They were like, right, screw it. We're not gonna form part of this cartel and keep the airline seats artificially high so that we can retain our business model. No, we'll have 99-cent seats. Yeah, screw it. Was their sort of disruptive attitude, and it worked incredibly well. And I think you have to have, you know, big cojones to sort of pull this off. But, you know, I don't think we have all that much to lose here. So let's do it. Let's do it.
No more questions?
All right.
Okay. So thank you, Gav.
You're welcome. Thank you.